Yeah. So today I talk about efficient fine-tuning. And so the first 1 or 2 years I got into machine learning, I was basically self-taught, and I benefited a lot from open resources. I learned things on Coursera. I participated in Kaggle competition, got my hands dirty, building machine learning models, collaborating with others. And I read papers on arXiv. But if you want to learn about language models, you can still access the courses and still read papers. But if you want to get your hands dirty, it's actually quite complicated. Language models get better as you scale them up. But if you scale them up, they're also much more difficult to use. So if you take the best open source models that are out there, you need dozens of consumer GPUs, 10,000s of francs to really get started. And so what I do in my work is basically reduce the cost of using these models and fine-tuning these models by compressing them. And so I want to make models more accessible so everybody can use them, get their hands dirty, really try to figure out when do these models break, how can I fix them, how can I improve them. And so I will talk about QLoRA, which is a method where you fine-tune a model, customize the model, personalize the model based on some new data set. And before I talk about QLoRA, I'll give you a little bit of background. So I work mostly in quantization. And quantization is a form of compression. And there it's important that you want to compress your model, but you don't want to degrade the quality of the model. And so before I dive into all the details, I will give you a little bit of background on that. And so first of all, what is quantization? So quantization is if you have a real value or an analog signal and you want to digitize it or discretize it. And it's very similar to histogram binning. So what I have here is in red a normal distribution. And then in blue, I have 16 different bins, and this is equivalent to int4 quantization. Int4 has 16 different values, and so how you quantize all the values in a normal distribution to just 16 different values is you find the minimum and maximum, then you slice the normal distribution in 16 slices with equal width, and then you take all the numbers contained in the slice and quantize it to the middle value of the bin. With this, you can quantize the entire distribution just with 16 different values. And that's how you do int4 quantization. In my work, I go a little bit beyond that. So what I do is I invent new data types that are specialized for neural networks. And so to work with them, I generalize in the concept of a data type. You can see it as mapping a binary representation to a number. And so to make them comparable, what I do is I normalize the numbers that these bits represent. Sorry, that was the microphone. The numbers that these bits represent, I normalize into the range -1, 1. So then you can compare all different kinds of data types. And if you want to quantize with this sort of representation, you follow like a simple two-step program. First, you want to take an input tensor x, normalize it into the range of the data type, which in this case is -1, 1. It's arbitrary, but we need to normalize into the same range. And then you take each element of the tensor and find the closest value in the data type that you have. Just to give you a simple example of this, here we have an input tensor 10 - 354, and we have a little bit weird data type in 2-bit, -1.0, 0.3, 0.5, and 1.0. And so we now go through these steps. The first step is we find the absolute maximum value to normalize the input tensor into the range -1, 1. And then we get -0.3, 0.5, 0.4, and then we find the closest value in our data type. And then when we have it, we can basically take the index, which is a bit representation. And that's then basically an int2 value that we can store efficiently. And if we now want to undo this and get our original numbers back, what we do is we load the int2 representation, look up the corresponding value in the data type, and then we undo the normalization by multiplying by 10. And so what you see here is that you get 10, 3, 5, 5. And if you compare it to the input tensor, we made one big error. The -3 turned into a 3. And so we see that this data type is not good for this input tensor. And this is sort of the general thinking. If you have a particular problem, you want to design a data type that's really good for this problem. And this is an example how you can think about sort of this problem. Here, I invented a data type that's very good of representing ratios. And so if you have a ratio with the numerator and denominator, you can have very quickly very small values, but also very large values. And so you want to have very high precision for these extreme cases. And what I invented is a data type that has a dynamic exponent. And so how it works is, it's an 8-bit data type, so we have 8 bits. The first bit is a sign for negative or positive. And then the first 0 bits indicate the exponent of 10 to the number of zeros that you have. And then the next bit is a 1. And this is just an indicator bit that indicates that all following bits are bits for the fraction. And so what you can do with this data type is, as you slide this indicator bit from left to right, you can determine how large is your exponent. And so with this, you have a dynamic exponent. You can have very, very tiny numbers, but then also large numbers with a large fraction. And so with this, you have both the small numbers and large numbers with high precision. Intermediate numbers have sort of higher errors. But this data type is very good if you want to, for example, represent a ratio. And again, if you have a problem, you want to design a data type that's good for this problem. Another concept that's important in quantization is outliers. In some engineering fields, if you encounter outliers in quantization, you can just remove them, and it's fine. It's some measurement error. In neural networks, it's not the case. Outliers usually represent very important values in the neural network. If you remove them, the neural network no longer works. And so what I have here, just to represent what happens in quantization if you have an outlier, I have an outlier at -10. And we have the same quantization as in the beginning. And now you see between -10 and -3, there are no bins. Or the bins that are there, they have no values. And that means that we need to squeeze all the other numbers in fewer and fewer bins. And how to think about it is if half of the bins are empty, you basically waste 1 bit of information. So your 4-bit data type suddenly turns into 3-bit. And your error increases a lot. And so to prevent this, you can use blockwise quantization. And it's very simple. If you have an input tensor, you slice it into small segments, and now you quantize each segment independently. So each segment has its own absolute maximum normalization constant. And so what happens then to an outlier is an outlier is confined to one of these segments or blocks. And all other blocks that do not have outliers, they are unaffected. And so they have high precision. And this one block has a bit lower precision, but it's confined to this one segment. And that's quite important to take care of outliers. And so these are the basics concepts. Now we go to a little more advanced concepts. This is about the quality of the quantization. How many bits should you use for parameters? And there's this trade-off where you can have, for example, a 10 billion parameter model in 8-bit, or a 20 billion parameter model in 4-bit. These have equal amount of bits, but the question is, which one is better? And so I wrote a paper, K-bit inference scaling laws, where we answer this question. And so what you see in this graph is, on the x-axis is the total amount of bits in the model. On the y-axis, you see mean zero-shot accuracy. So we ask the model some questions, give them some prompts. We score how often it's correct. And this is across 4 tasks. And in colors, you see the bit precision of the parameters. And so you see that the information density, how much performance we can get per bit, increases if we decrease the precision of the parameter. So if we go from 16 to 8 to 4, performance improves. But if we go to 3, performance degrades. And we get these jagged lines, which are instabilities in the quantization. And so from this plot, if you have just the information of the weight, the best you can do is always quantize in 4-bit precision. With that, you maximize the information density per bit. And if you want to improve this, there are not so many things you can do. One thing is to look at the block size. So again, blockwise quantization, where you slice up your tensor. If you go smaller and smaller blocks, then you improve the performance. This looks, on this plot, looks sort of like small improvements, but they are quite significant. One thing to note here is the smaller you have a block size, the more significant is also the memory overhead. For example, if you have a block size of 64 and your absolute maximum normalization constant is 32-bit, you add 0.5 bits on average to your overall neural network weights. And so the blue line here is actually not a 4-bit quantization, it's a 4.5-bit quantization. So the smaller the block size, the more the overhead, and that's also important to think about. Then the other thing, and that's sort of also what my research is about, is if you use specific data types that work well with neural networks, you can improve the information density. And so we see, for example, integer is not such a good data type. Dynamic exponent that I developed for ratios is also not so good. But floating points and quantile quantization, which is an information theoretically optimal data type for neural networks, that works quite well. And so these are the core insights. And particularly the last one about sort of the scaling behavior, all these insights made it into QLoRA. And QLoRA is a very efficient fine-tuning technique. And let's dive into the details there. And so the main motivation, as I said before, is we have now these big open source models, but they're very difficult to fine-tune. So if you want to customize them, you need like dozens of consumer GPUs or data center GPUs. And so if you look at where does the memory come from, it's mostly from the weights and the gradients that we have when we optimize the entire neural network. And so we have 2 bytes from the weights, 2 bytes from the weight gradient, 8 bytes from the optimizer. That's 12 bytes in total. And that adds up to 840 gigabytes of GPU memory if you want to fine-tune a large model like the Llama 2's 70 billion. And so there's more efficient fine-tuning with low-rank adapters, where you only adapt a small portion of the neural network. And there still the weights are on 2 bytes or 16 bits. Then the other things, it's only a couple of bits, fractional bits on average. And that adds up to 17.6 bits per parameter. And that's still 150 gigabytes of GPU memory. So you can't do this on a consumer setup. You need multiple computers. And that's complicated, that is expensive. And so to improve this, to basically bring everything to a single GPU, what we do is we invented QLoRA. And in QLoRA, you have low-rank adapters, but now the difference is that the base model is quantized to 4-bit. So you have you take a pre-trained model like Llama 2, 70 billion, you quantize it to 4-bit, then you put low-rank adapters on top. These usually have a higher precision, 16-bit, but they're tiny. And so if you fine-tune the model, you backpropagate through the frozen model into the adapters that are adapted during fine-tuning. And if you have this setup, it only consumes about 5.2-bit on average. And that gives you 46 gigabytes. And that fits on a single sort of low-grade data center GPU. Someone on Twitter that's very active sort of in the local Llama community, Alyssa Vance, she actually also fine-tuned a 70 billion model with context lengths of 4,000 tokens. So this is like to the max, and she does it on a single consumer GPU. And this is very impressive. And so just a couple of years ago, that was like the biggest model sort of equivalent performance that you see in industry. So with these techniques, you can very quickly have access to very large and powerful models. And yeah, so that is the motivation. We want to reach this, and with QLoRA reach this. So how does QLoRA work? And so there are 3 main components. And so the first component, it's a little bit elusive, and this is a component that works in the background to prevent memory errors. So if you train a neural network, usually your documents have a smaller length or a longer length. And so the maximum memory footprint is usually determined by the longest document that you have. And sometimes you train for half an hour or maybe a day, then you hit one of these long documents and your model crashes because you get an out-of-memory error. And so what we developed to prevent this is similar to what you have on computers between the CPU and the disk, is swapping. So if you hit a memory, a long document that throws an out-of-memory error, what we do is we take a portion of the optimizer state, which consumes quite a bit of memory, transfer it to the CPU, then we have new memory that can be allocated for gradients or other things that are needed. Then we complete the forward pass or backward pass. And then if we do the update on the optimizer, what we do is we swap back from CPU back to the GPU. And so with this, we have like a completely fail-safe and lazy option where you can start your model. And if you know it starts, you know it will run. It will not crash. It will not run out of memory. And this is paged optimizers. That makes running neural networks very easy. Then the second thing is just to reduce your overhead. And as I said, if you have blockwise quantization, it can add quite some memory overhead. So if you have a block size of 64, it can use half a bit of information. And so if your models are very large, that can be gigabytes. And so to really compress models down to fit on a consumer GPU, we invented something silly, and this is double quantization. So if you quantize, you have the quantized weights and the scaling constants. What we now do is we take the scaling constants and just quantize them again. And so if you do this, it saves about 0.4 bits of information per weight. And that's a couple of gigabytes. And that is actually important to make it fit on consumer GPUs. And then the last thing is we develop a new data type. This data type is information theoretically optimal for normal distributions. And basically, weights in a neural network are normally distributed. So with that, it makes it information theoretically optimal for neural network weights. And so how it works is instead of having slices with equal width, you want to have slices of equal area in a normal distribution so that each slice has equal amount of values in it. And so if you have that, it's information theoretically optimal. And you do this through the quantile function or the z-scores of the normal distributions. Then you normalize it in the range -1, 1. And then you have the data type. We call it normal float, 4-bit normal float. And that is sort of the last ingredient. And so with this, we have now QLoRA, which fits very neatly. And we have this sort of high-performance data type. And so now it's a question, do we need all these components? And sort of the first thing is that we look at is the 4-bit normal float. Is this data type really good? Does it help? And so here we again have a scaling law plot with total model bits on the x-axis and on the y-axis mean zero-shot performance. We compare the float with the normal float and also normal float with double quantization, DQ double quantization. And so we see the information density improves if we use the normal float. So yes, this data type seems to help. This is for different llama models. We also tried in the table for different kind of models. That's not only llama models, also OPT, Bloom, and Pythia. And so there we also see that the normal float gives much lower perplexity on average, which means better performance. So yeah, this data type works, and it helps. It improves the performance if you want to really compress your models. You can preserve more of the quality. And we do further sort of analysis on this. If we do adaptive fine-tuning on different kind of models, and these are a lot of numbers, the important thing is basically the last column where everything is averaged. And so we have here llama models that we fine-tune on instruction data sets. So to follow instructions in the data set. And so we have alpaca and flan too. And if we fine-tune on these and average all the results, we see that to replicate the 16-bit performance is actually important that we have the normal float data type. And so with this, we've shown that we can compress models down, and if we have the right data type, we can preserve the quality of 16-bit transformers. And so now we have very small models that are very efficient to run, that replicate full performance. And so what we can do with this, run lots and lots of experiments because it's so cheap now. Many papers many academic papers, if you look at instruction fine-tuning, they maybe have 5 or to 10 runs. We run over 1,000 fine-tuning runs, and we really try to find out what is important in fine-tuning, what matters. And so we run over a couple of data sets, and we evaluate on MMLU. which is sort of a data set. It's a bit of reasoning, education, and that's about multiple choice questions and how to get it right. And so what we see is that some data sets are really good, like FLAN version 2 is by far the best. So these numbers are accuracies, so higher is better. We see also if we increase the model size, instruction fine-tuning seems to help less, but the FLAN version 2, we still improve over the baseline model. So FLAN version 2 seems to be a really good data set. But similar, so Julien already talked today about this. Evaluation is really hard. It actually turns out FLAN version 2 is not really good for chatbots. And so let me talk a little bit about chatbot evaluation. It's very difficult. Why is it so difficult? Because you have very open-ended questions. If you get the question, what are 10 tips that make me more productive? Then what is a good answer? How do you rate that? If you get a scale from 1 to 10, what is a 10? What is a 7? What is a 4? And so if you give this question and give outputs to humans, there's a lot of variation. It's very unclear what is a good answer. What works better if you compare two answers. If you have two answers, it's much easier to say which one is better than the other for this prompt. If you ask the humans, there's still a lot of variability. But you can also repeat this by asking a model like GPT-4. So you have a prompt, you have different chatbot models that give different answers, then you give those answers to GPT-4 and ask which response is better. And then ChatGPT says like, oh, the left or the right one is better, and with that you can determine a rank basically of chatbot performance. And we do this, and there are sort of existing data sets. Vicuña data sets has 80 samples. But as Julien said already before, this is like quite noisy, and you shouldn't trust a single benchmark. And because the benchmark is so narrow, you need to be very careful about how you present your results. So we developed a model, Guanaco, and it's actually better than ChatGPT on many prompts that we have. But our prompts are very narrow in this Vicuña data set. And so if you have a more broad evaluation, then you actually see ChatGPT is much better on average if you have very broad evaluations. But so that is our setup. And we also take it a step further. We develop a tournament-style benchmark. And there what you do is you have a prompt, then two chatbot models in a game basically provide a response. And then the judge is either a human or GPT-4, and then this judge determines the winner. And if a chatbot model wins, it either loses points or gains points. When it wins, it always gains points, of course. But with that, over time, you get a ranking, an ELO ranking in this tournament. And with that, you can determine what is the best model compared to other models. And so this is a lot of numbers. Our model is Guanaco in bold. What you can see is, and that's quite important, FLAN version 2 is at the bottom. It was the best data set for instruction fine-tuning, but for chatbots, it's the worst data set. And that's sort of the interesting thing, that it's what you fine-tune on is basically what you get. So you need to be very careful about what you want to get, how you evaluate it, and what is in your data set. The other thing is the Guanaco data set, it has only 10,000 samples. The FLAN version 2 has over 1 million samples. So data set size is not that important for fine-tuning. It's really the quality that matters. And that's sort of an important takeaway. And if we look at the Guanaco model, it works really well. Gets very close to ChatGPT performance. If we measure it relative to ChatGPT, gets close to 100%. And on the left, we have the tournament, and there it also does really well compared to other models, even beating ChatGPT. And because we quantize everything 4-bit, even these large models are actually pretty small, and you can run them on consumer GPUs. And so this is a bit more comprehensive benchmark, where you're not limited by 80 prompts that we evaluate on, but here in this setup is people on the internet always ask some new questions, so it's a very wide distribution. And our model also does pretty well. Guanaco, if you compare it to the memory footprint to other models, is actually the strongest model. And so that's what I have. So I've shown with QLoRA, we can make these models much, much more accessible. Now you can get your hands dirty and really gain the experience to really understand how to use language models and improve them. I've shown that with like the normal float data type, double quantization, we can compress the models, but also preserve the quality. And overall, that leads to a 17 times smaller memory footprint while preserving the full precision fine-tuning performance. And we have also shown that if you pick the right data, pick high-quality data, you can get very strong models like our Guanaco model. And that's what I have. Happy to take questions. Thank you.
Thank you so much, team, for this great input. Let's take some questions.
Hi, thanks for the great talk and the amazing contribution to the community.
Thanks.
I have a question. You know, there was this Sarah Hooker's paper at a while back on pruning that showed that sometimes when you remove a lot of information from model, like in the case of pruning, you also sometimes deteriorate the performance of the model in some part of the distribution. Have you observed the same type of phenomenon appearing in quantization when you get to extreme level as you do, or did you manage to preserve the whole distribution?
So yeah, a magic marker is sort of at 3-bit, things break down. Let me see if I can bring it up again. So here, 3-bit things break down, but you can actually do better if you consider the inputs. And I mean, at some point, there's a hard limit. I don't have it in my slides, but it's really, really difficult to get below 3-bit. So at some point, you have things just break down. You also have some smaller pockets of breaking down. So what we also see is that if you quantize models, you have some probability of really generating one bad token. And if you have one bad token, then it just goes downhill. Everything after it will be very crappy. And so I haven't seen any sort of particular domains or so that produce bad performance, but there's more like probabilistic way that you generate bad data. And the best protection against that is actually try to quantize your model and stay as close as possible to 16-bit performance.
Any other question?
Hello, thanks for the talk. You showed mostly about inference, quantization, but what do you think if you could do inference quantization when training from scratch model?
Yeah, so I also worked a little bit on sort of 8-bit training. I worked a little bit on language models and a little bit on clip training. And so what I can say there is a couple of things. There's a new data type, floating point 8, supported by new hardware, the H100s and Ada GPUs. And if you use that, it's pretty easy to train in 8 bits. So what we probably see in the next couple of months, people that have the new hardware, they will train in FP8. If you train in int8, it's a bit more difficult. There are a couple of things that you need to sort of take into account. For example, you need to adjust the optimizer a little bit and also adjust the scaling of layers so you can benefit from int8 compute while also sort of controlling the instabilities. But yeah, it's definitely possible to train in 8-bit. If you're going to want to go below that, a very difficult problem. I don't think we get there anytime soon. At that point, you also have sort of this trade-off that you can no longer be close to 16-bit performance. It's more a question of, if you look at the overall hours of compute that you have, can you get a lower loss? And yeah, that will be a research challenge for the next couple of years.
Thanks a lot. In the meantime, I'd like the panelists to join us on stage, if they're around, and we can take maybe one more question from team in the meantime.
It's a bit of a crazy question along the line of how small we can go with bit precision. So I really liked the way you described that it's better to maximize the number of parameters and minimize the bit precision. Can we go down to the bottom of like a 1-bit model with a lot of parameters?
Yes, so we have one work where we already try like sort of, one thing is you can do just a quantization, have like low bit weights, but then you can sort of add auxiliary parameters that are sort of in higher precision. And so one thing we do is we extract a sparse mask of very important values, and then we do a dense matrix multiplication that's sort of quantized, and a sparse matrix multiplication with high bit values that are really important, but it's like you have like 1% of the overall size of the dense matrix. If you do that, you can do better. And then there are also some certain pockets, for example, mixture of expert, they're much easier to quantize. So there you can actually go to 1 bit. But what I'm seeing right now is it's similar to what I said before. It's very difficult to go below 3 bit. So it seems everything below 3 bit will be very difficult. I think we will get close to 3 bit, but that's probably the most practical limit, because at some point, if you add more and more things, it becomes also slower. And so just compressing the neural network is not enough. It also needs to be usable, and for that it needs to be fast enough.